Please join me in welcoming Dr. Catherine Bowman. Thanks for joining us, Katie.
Thanks so much for the kind introduction, Jennifer, and thanks for inviting me today. I'm really looking forward to telling you a little bit about some of the work myself and my colleagues have done, as well as kind of chatting with you afterwards, answering any questions you might have. And I also heard that there are some high school students in the audience, so I really want to encourage some of the younger students to also ask any questions you have. I'm really looking forward to talking with you more. So today I'm going to tell you how we took the first portrait of a black hole and kind of what is to come in the world of black hole imaging in the coming years. And so, many of you have probably heard of black holes, but they are still very mysterious. So black holes are one of the most mysterious phenomena in our universe, and scientists have been studying them ever since they were first predicted from Einstein's theory of general relativity just over 100 years ago. And in particular, for decades, scientists have been studying this giant elliptical galaxy that's at the head of the Virgo constellation. This galaxy is called M87, and it's 55 million light years away from us, and very special because over 100 years ago, someone discovered this streak of light on the sky, which ended up being a galactic scale jet of plasma that was shooting out of the core of the galaxy of M87 and marking the spot of a supermassive black hole. And so over decades, scientists tried to develop better and better instruments to try to study the supermassive black hole to be at its center. And then in April of 2017, we hooked up this Earth-sized telescope and collected the data necessary to make the first picture of a black hole. And 2 years later, after processing the data, this is what we saw. So as many of you probably know, this black hole image was the result of a group of hundreds of scientists from all around the globe that worked together to build this computational Earth-sized telescope that could take the very first picture of a black hole. And so today I'm going to tell you an abridged story of how we were able to capture a picture of a black hole. And, and I'm sure some of you have heard different parts of this story before, and there are many kind of different angles to it. So today I'm going to give you a glimpse into kind of my primary contribution to the story, how the imaging process was done and validated. And then at the end of the talk, I'm going to go into a little bit more about techniques that are currently being developed in my group at Caltech to push the Event Horizon Telescope past its current limits to see environments around black holes that are still invisible to us even now. And in particular, I'm going to talk about how we're developing new artificial intelligence, machine learning methods to optimize the placement of the next telescopes we build into the Earth-sized telescope array in order to see what is still invisible. But before we get there, the first question you might kind of ask is, well, what does it even mean to take a picture of a black hole that by definition doesn't let light escape, and so it should be unseeable? Well, light propagating near a black hole doesn't actually follow straight lines. It's curved because the black hole is curving space-time. And so photons can even go in complete circles around it. And so actually the space around a black hole is lit up by this hot gas that's spinning around. It's heated to hundreds of billions of degrees. And so we have lots of photons flying around everywhere. The ones that are too close or pointed towards it fall in, but other ones just graze it so that they're bent around. And the net effect is basically that the black hole casts the shadow on the bright surrounding emission that's almost perfectly circular. So we're not seeing the black hole itself, but we're seeing the imprint of the black hole on this backdrop of hot gas. And if Einstein was right about general relativity, this light would be bent into a ring whose size and shape tell us about the mass and the spin of the black hole. And this ring is often referred to as the black hole shadow because it's like the black hole is casting a shadow on that bright emission. This is a more realistic simulation of what the turbulent plasma and the jets and the accretion disk around a black hole, what we think it would look like if we could see at a very, very high resolution and we could see at about a 1 millimeter wavelength. But even if we know that the black hole should, even if we expect that the black hole should make an imprint on the gas around it, taking the picture of this ring is incredibly difficult. What makes it so hard? Well, M87 is, it's so far away from us, so it's so small that even the Hubble telescope can only barely make out this booming jet on the sky. And so seeing the black hole shadow requires a very particular type of telescope, one of just the right size and observing at just the right wavelength. At too short of wavelengths, like optical wavelengths that we and the Hubble sees, the light is blocked from reaching the Earth from the core of the galaxy by dust and other kinds of things. And similarly, at long wavelengths, gas that shrouds the black hole blocks all the light from within. So this is a simulation of what we think a black hole looks like at a 3 millimeter wavelength. And even at 3 millimeters, the event horizon is not visible. That ring of light isn't visible, but as you go to shorter and shorter wavelengths, theorists predicted that eventually this gas would become optically thin, and we would be able to see that event horizon, the imprint of that event horizon. So even if you could successfully observe at this short wavelength, we face another huge challenge. And that's that the size of this ring is incredibly small. It's about 40 microarcseconds in size, which is about the same size as a grain of sand, but if that grain of sand is in New York and I'm viewing it from California. And so taking a picture of something that small is really, really hard. And the reason why all comes down to what is called diffraction. So diffraction says that if we put in the wavelength and the required angular resolution we need to see that black hole shadow into this diffraction limit equation, we can calculate that in order to see that black hole ring, we need to build a telescope 13 million meters across, or essentially the size of the Earth. And if we could build an Earth-sized telescope, we could just start to make out this distinctive ring of light that's indicative of the black hole's event horizon. Okay, well, obviously building a single dish telescope the size of the Earth is impossible. But by joining telescopes located around the world, I've been working as part of an international collaboration called the Event Horizon Telescope that built a computational telescope the size of the Earth, capable of resolving structure on the scale of a black hole's event horizon for the first time. Joining telescopes in this way is a technique called very long baseline interferometry, or VLBI. So how does this computational telescope work? How do we join signals from these different telescopes? Well, these telescopes are actually linked through the precise timing of atomic clocks. So we put specialized hardware in different telescopes around the world, and then we have teams of researchers that essentially freeze the light. They travel to the telescopes and they freeze the light by recording petabytes of data that are time-stamped by these atomic clocks. And then we bring all that data together and use our computers to act like the lens to make the picture. So how do we do that? How do we get the picture from that data? Well, unlike with a camera, in the Event Horizon Telescope, we don't capture the picture in pixel space, but instead in its frequency space. So we essentially take measurements of the black hole image's Fourier transform. If you know what a Fourier transform is, you might get some idea of what those measurements might inform us about. But if you don't know what a Fourier transform is, that's okay. Just think about it as we want this collection of measurements that tells us about the picture. And if we put telescopes all across the globe, we would sample all these different spatial frequency measurements. But since we only have telescopes at a very few locations, we actually only get a sparse number of measurements. And so it turns out that for every 2 telescopes we have in our telescope array, we obtain a single complex measurement of the underlying image's 2D spatial frequency related to the projected baseline between the telescopes. So in other words, the measurement we make is related to that projected baseline, and we only have a few telescopes. I do want to mention, though, that this is a complex number, which means it can be described by an amplitude and a phase, which we'll talk about in a little bit. So it's good to keep that in mind. So in 2017, the Event Horizon Telescope actually had 8 participating telescopes, but of those 8, actually only 5 of them were able to see the black hole in M87, and were at different locations. So with the EHT's 5 telescopes, that would only sample at most 5 choose 2, 10 different points, 10 different measurements that would be an incredibly small number of measurements to try to recover an image from. But luckily, as the Earth is rotating, we actually obtain new measurements. So since the projected baselines between telescopes change as the Earth rotates, this amounts to carving out different elliptical paths in the spatial frequency plane, where telescopes that are close together tell us about broad structures in the image. And so to get the fine detail we need to see that ring, we have to put our telescopes as far apart as possible. So once we get these measurements, how do we get these measurements? Well, we get them by recording about hundreds of terabytes of data at every telescope. And so here you can see my friend Lindy Blackburn posing with about only half a petabyte of data that we collected at just the LMT telescopes. We have many petabytes, and then we have record so much data that we can't send it over the internet, and it's flown to a common location. And at that common location, we use a special purpose supercomputer called a correlator that combines the precisely timed data. And then once this is done, it's passed to a calibration stage, which finds weak signals hidden in the correlator output by tuning parameters to extract a stronger signal. And developing this calibration pipeline for the unique EHT data was like a huge endeavor. We had to design new algorithms, new ideas in order to deal with the messy data we got from the Event Horizon Telescope. And this effort was led by Lindy Blackburn, but with a lot of help from others, including CK Machik, Sarah, and Michael here. And this was an essential part of getting the data that we could then use to make an image. So once we get this data, then how do we go back and solve for the image that caused it? So this is a bit more on the topic that I worked on of how do we turn those measurements into an image. So at this point, we have the data and we can kind of abstract away all the astrophysics of the problem and think of it as a purely mathematical problem. We have the sparse data and our challenge is to find the image that caused it. And if we were given measurements that covered the entire frequency plane, the entire measurement plane, it would be trivial because in the case of no noise, we would have all the measurements we'd need, and we just simply need to apply an inverse Fourier transform to get back the picture. But since we only have a few samples, there are therefore an infinite number of possible images that are perfectly consistent with the data we measure. And on top of that, the fact that there's a different and quickly changing atmosphere above every telescope across the globe causes our data to be very noisy. So I'd like to give a little bit of intuition for how this noise enters our system because it tells us later on how we kind of approach the imaging process. So the whole reason the Event Horizon Telescope works in the first place is due to the fact that light coming from the black hole, it's going to travel to Earth for 55 million years. And then it's going to reach one telescope slightly before the other one. And that slight time delay is key for extracting those 2D spatial frequency measurement that's used for image reconstruction. But when you have a telescope in Chile and one in Spain and one in Hawaii, they all have different atmospheres above them. And those different atmospheres add an additional random propagation delay in the time it takes the light to reach the telescope, which leads to an additional phase delay in their frequency measurement. And similarly, the atmosphere causes a different attenuation factor in the signal, causing a changing absolute gain term. So this error is very challenging because ideally we would measure this nice, beautiful, complex Fourier component, the italicized V here on the right. But in reality, we actually have a completely random phase error that's included on the measurements, and sometimes a pretty bad amplitude error as well. And so that's pretty terrible because at first glance, it looks like we've lost both our amplitude and phase information. And so if you've lost both amplitude and phase, and that's all you have for every measurement, then what really do you have left? But luckily, there's some structure in these measurements that we can exploit. So if you look at the measurement term of how every measurement is made, you'll notice that these errors are site-based. So remember that every measurement we make comes from two telescopes. It's that projected baseline. So every two telescopes gives us one measurement. And if we have a third telescope, then the measurements that are formed with that third telescope share some of the same corrupting terms, G2 and phi2. And so we can design algorithms to take advantage of this redundant corruption when solving for our images. If some of you are familiar with what phase retrieval is, we're essentially having to solve a constrained phase retrieval problem. And so to do this, we developed two classes of imaging algorithms to tackle the problem. The first class of algorithms is based on very standard methods used in the radio interferometry community. The method's called clean with an iterative self-calibration loop. And this is the traditional method of making images, which is a huge plus because it's well understood in the community, it's vetted in the community, But the disadvantage is that it was originally designed for telescope arrays that have more telescopes or less noise. And so for the Event Horizon Telescope data, you often need a significant amount of guidance from a knowledgeable user to guide it in the right direction. There are many people that worked on imaging on developing methods for clean, but I want to highlight Jose, Jae-Young, Thomas, Allen, Svetlana Shoko, among others, who really got these methods working on the EHT data. The second approach of methods is methods that we've been developing more recently, and this is what we call regularized maximum likelihood. And I've been primarily working on this type of method, along with people including Michael Johnson, Andrew Shale, and Kazu Akiyama. And in this regularized maximum likelihood method, we don't try to find an inverse function that takes us directly from the measurements to a picture, but instead we try to find a picture that both fits the measurements and is what is defined as likely through some sort of prior or regularizer term. And so the disadvantage here is that we have to define what is a likely image, and that is always going to introduce bias. But the huge advantage of these methods is that we can naturally incorporate lots of different kinds of error that we expect to see on measurements from the EHT that are not naturally dealt with in the traditional clean method. And so just to briefly summarize the regularized maximum likelihood approach, kind of the idea is we model the forward telescope system as a function f of x that returns the data that we would likely see y hat if the true image in the sky were actually x. But since we do not observe all possible measurements, since we have sparse data, there's going to be an infinite number of images that are going to give us exactly the same y hat value, making the problem ill-posed. But although there are an infinite number of solutions that are equally likely in terms of the measurement likelihood of the images that are consistent with the measured data, there are some images that are more likely than others. For instance, perhaps we think the image on the left is too messy, and we prefer an image that is sparse or compact like the one on the right. Thus, our goal becomes to find an image that doesn't just fit the data, but is also likely under some sort of model of good or likely images. And so using this idea, we incorporate what we call an image prior or a regularizer term that essentially scores each image. And so by solving for an image that maximizes both the data likelihood and the image prior, we can whittle down from the infinite possibilities to a single one that we think is a likely image that fits the data well, even in the presence of all that kind of crazy atmospheric noise I talked about. Okay, but note that even if we can develop these methods such as these ones to recover a single image, we always have to be cautious. And that's because any method we come up with, whether it's a regularized maximum likelihood approach like I'm showing here, or a fancy new machine learning approach, it's going to require that we always inject some additional information into the problem about what images look like to recover something back in the end. In the case of the regularized maximum likelihood problem, it's through that prior that's highlighted in yellow that tells us which images to prefer. In the case of a machine learning approach, it might be the images that we use for training data. And this injection of additional information is always going to bias our final picture. And we wouldn't want to accidentally, for instance, have a preference for ring images and then be super excited we recovered a ring back in the end. And so that meant a big question we faced in dealing with the M87 black hole data was not just how to make an image, but also how do we verify that what we are reconstructing with our imaging algorithms is real. And we tackled this through a multi-step process. The first step actually began years before we had even collected the data of the black hole, and that was to run synthetic data tests. We did this through challenges that we called the Event Horizon Telescope Imaging Challenges, and in these challenges, we'd have a team of people simulate realistic data sets that were then distributed so that anyone could try to make an image from them. The data sets were distributed without any information about what the true image was used to generate the data. So we basically have a computer simulation of what the telescope might see, given we put some image in the sky, we send out these mock data sets, and then we'd ask people to use their algorithms to try to make their best guess at what the true image is. Once we got these images, we actually passed them off to a group of astrophysics experts that we'd recruit to try to predict what the underlying structure of the true image is. And this was essentially what was going to have to happen when we were working with real data. Since we didn't know what the true source is, we'd have to use our imaging algorithms to try to make our best guess at the true underlying structure. But unlike in the real data case, because the data is simulated, we could also evaluate how accurately the reconstructed images match the true image. And so we learned a lot from this process. I want to show you a few examples of things we saw in these imaging challenges that helped motivate how we actually went about imaging the real M87 black hole data. So here is one example. On the top is the true image that was used to generate data, but this was hidden from the people who were trying to make the images. And on the bottom are 5 different submissions that were made independently by different groups of people. And you can notice that in each submission, each image looks slightly different. Some of them have look more piecewise in structure. Other ones have different wispies in different places. But if you look at them, they all kind of have a similar structure of this kind of crescent shape that's brighter on the left side than the right side. But by looking at what was similar and different across them, we could try to gain confidence in certain features and reject other ones, because every method has preferences for different kinds of structures. And so by looking at what is similar and different, we could try to tease out what was real and what was likely fake. But we didn't want to just test ourselves on images of things like that we'd expect a black hole to look like. So we also threw in some random things that too. Here was a submission for another challenge. And the reason I like to show this example is because clearly no one was expecting the snowman to be in the center of the galaxy. And obviously our imaging methods aren't expecting anything like that either. But we were still able to get this kind of surprising Frosty the Snowman structure. And that gave us confidence that we would be able to get something surprising in our real data, even if our interpretation of it might be way off. But it allowed us to show that we could have, our methods were flexible enough to show something exciting. So based on these synthetic data tests, we developed how we were going to approach the actual M87 data. We wanted to avoid shared human bias like we had done in the imaging challenges in order to assess common features among independent reconstructions. So to do this, we split about 40 people who worked on imaging into 4 different teams. These 4 teams actually span the Earth. And when we got our data, when we were handed the data for the M87 black hole, what we did is we actually decided, okay, let's go into our respective rooms with our teams and let's try to make our best images from the data without talking to any of the other teams. So we worked in isolation, trying to make our best image from the data. And then after 7 weeks, we all gathered together in Cambridge, Massachusetts, and we revealed the images to each other. And this is what we saw. So this was quite amazing because similar to in those imaging challenges, each picture is different, but they all still reconstruct this same basic structure, a ring of roughly 40 microarcseconds that's brighter on the bottom than the top. And seeing these images was one of the happiest moments I've had in the collaboration because it brought a whole other level of confidence to the results as we found the same structure no matter what method or person reconstructed the data, and these were done independently of each other. And so without having done this test and having had different people reconstruct with different methods, we would never achieve this the level of confidence we have in our results, I feel. But we still wanted to make sure we weren't imposing human bias. Just because we had avoided shared human bias through this test, that doesn't mean that we were avoiding human bias altogether. So we spent the next couple of months essentially trying to break these images. And that led to the third step, where we tried to objectively choose image parameters to remove humans from the loop as much as possible. To do this, we developed 3 different imaging pipelines. These imaging pipelines, you can actually download them online along with the data, try to run these methods on them, make your own methods, improve ours, what have you. But we built these pipelines to have different knobs on them, hyperparameter settings that are usually tuned by a human user. But instead of having a human tune the algorithms, we instead wanted to search for the best set of knob settings to recover different kinds of source structures. So for instance, we generated synthetic data as if the Event Horizon Telescope were actually seeing a disk on the sky with no hole in the center. And we found the best parameters beta to recover this disk shape. And then when transferring these exact parameters onto the M87 data, we found that our algorithm still required us to put a hole in the center, even though we had tried our hardest to find beta parameters of that disk with no hole. And by doing this simple training and testing procedure on different kinds of underlying sources, we saw that our methods always preferred the ring shape. And that was true no matter the day we observed M87 on or the imaging code we used to reconstruct it. And so by blurring the images from different imaging pipelines to an equivalent resolution, we then averaged them together to form the image that we showed the rest of the world in 2019. This ring of light surrounding the black hole, roughly 40 microarcseconds in size, and brighter on the bottom than the top. So we're so excited to see this, but we still weren't sure. And so we went through a number of different validation tests. We did a lot of these. I'm only going to really briefly talk about one of them. But obviously we have outlined all these in the papers that we wrote along with the results. So previously I talked about how we selected one set of parameters, beta here, that perform best on synthetic data. But why really should there only be one parameter setting that we consider? In fact, by doing large parameter surveys, we found that there are often many parameters that actually perform reasonably well. And so instead of just selecting one beta, instead we set a threshold, and we found all of the betas that performed above that threshold on synthetic data, and then applied those parameters to the real M87 data and found how that affected the images that we got out. So for example, for one of those imaging pipelines, we ran hundreds of thousands of simulations, and we found about 1,500 parameter settings that we deemed acceptable. So for example, here is a slice of 2 of the parameters that we searched over, and the green boxes show a selection of images that we identified as reasonable through tests on different synthetic data sets. And then once we had these images, for instance, the 1,500 for that one survey I talked about, we could look across them for variations. So actually, if you align them and you look at, for instance, the standard deviation, you'll see that actually there is variation of the flux that we recover along that ring. So there's these, for instance, these 3 knot regions along the bottom of the ring that have more uncertainty. But if you look at the standard deviation, the value of that standard deviation relative to how bright that ring is, so by looking at the fractional standard deviation, you can see that actually we really trust that ring structure, although there are slight perturbations and uncertainty along the exact value of the brightness of the ring. That ring appears in basically all images. But what we don't trust is all that wispy structure on the outside, because that changes a lot depending on those imaging parameters. So overall, tests like these showed us, okay, this ring is real. And that's a very exciting thing. It's very exciting, maybe it seems obvious now, but it's very exciting that we were able to actually recover a ring like scientists had predicted. But what have we learned from it still? So one question you might ask at this point is, did we prove Einstein was right? And well, the short answer is no, we didn't, but we also didn't prove he was wrong, which is also a big deal. So I want to talk through how we can use this image to help us understand more about black holes and gravity. So if you take a fixed size mass, we can actually calculate the radius we need to compress that mass down to in order to get a black hole. For a non-spinning short-shelled black hole, this is also called its event horizon. But actually, generally what we expect to see is not the event horizon itself, but the point at which photons are orbiting around that black hole in stable orbit. However, not even that is what we expect to see, because due to the immense gravity around a black hole, this photon orbit is actually lensed. So if you it becomes bigger as those photons swing off of it and come towards it. They're lensed out to a ring that's about 5.2 times that short-shelled radius. And if the black hole is spinning, it appears a bit smaller. So this is the range of diameters between 4.8 and 5.2 times the short-shelled radius. That is the range of diameters we'd expect for a black hole obeying canonical general relativity. And notice that this directly depends on the mass of the black hole. So for a smaller mass black hole, this ring actually becomes smaller because it's depending on m, that mass. And that's interesting because actually from past measurements of M87 mass, it was very unclear what the mass was. Gas dynamics pointed us to around 3.5 billion solar masses, while stellar dynamics pointed us more to about 6.5 billion solar masses. So a big difference in those estimates. But stellar dynamics really provided an upper limit, since there couldn't be more mass within the stellar orbits than from the black hole. So we wouldn't expect a ring any bigger than this yellow one. But then we could ask ourselves, okay, how do we turn this into a test of black holes? Well, we can look at other unusual exotic objects. For instance, wormholes also produce shadow features, but wormholes also have a smaller shadow than a black hole. And naked singularities or super spinning black holes also produce shadow features, but they'd even be much smaller. And it turns out when you lay the Event Horizon Telescope on top of image on top of all these different predictions, you instantly rule out all these other kind of exotic possibilities, and you're left with a ring that matches nearly perfectly with the stellar dynamic measurement of the black hole mass for canonical general relativity, a mass of about 6.5 billion solar masses. But what exactly is the mass? Well, we can take this equation for the diameter and relate it back to the mass. But remember that this diameter is for a very particular diameter, that one of the photon orbits, where the photons are orbiting multiple times around the black hole. And if you look at a bunch of simulations, you'll notice that sometimes most of the emission is actually from gas flowing outside of that photon orbit, not the photon orbit itself. And so groups at Radboud, UIUC, Frankfurt, and Harvard and Perimeter got together, and they made this huge library of simulations. And then by simulating the data from them and like making mock data sets from our Event Horizon Telescope simulator, and then doing feature extraction on these synthetic data sets, we could figure out how to calibrate the mass to the recovered diameter. And by applying this calibration to each of the different ways that we recover diameter, from a number of different kinds of ways, we found that no matter the way that we did it, we always got a mass of about that agreed with the stellar dynamic measurement of about 6.5 billion solar masses. Just want to highlight some people here who were critical to this analysis. Avery Broderick, along with a number of his students, but especially Paul, I want to highlight, Don Pesci, Jason Dexter, and Ferio Ozel. So this is just one of the many things we can learn about black holes and gravity by studying this image. But perhaps the most amazing thing we see is that by comparing this picture to simulations scientists have made for years, we find the image that we've taken is amazingly consistent with a number of these predictions. But you might notice that the simulation I just showed you, it was moving. So is our recovered image of M87 also moving? Well, in fact, it turns out it is. So another interesting thing is that we actually observed the M87 black hole over 4 different nights over the course of a week. And if we took each night of data and we independently imaged the black hole image that comes out of each night, and we strung them together to make a movie. And if you play it together, you'll see there's some variation, some evolution in the light around the black hole. So I'll play it for you here. It's really hard to see, so I'm going to play it again. You'll see that the bright spot moves a little bit more from the left, more down to the bottom. So I'll play it again. So we don't have a good idea of what exactly is causing the variation. Is it rotation or just material lighting up? And we're even unsure of where it appears in the image domain. But what we are really sure of is that that variability around the black hole actually exists. And that's because it appears in the raw measurements we take. So if you look at something, these measurements, you'll see that there is a very significant difference between them. And so that means that something has to have changed around the structure of the black hole, the gas and where it is bright has to have changed. And actually getting a hold on a black hole's time variability is really important for a number of reasons. It not only gives us a window into the dynamics around a black hole, and hopefully an understanding of how these powerful galactic jets are forming, but it also helps us in mapping the space-time of a black hole and constraining our prediction of general relativity even further. But actually, the black hole in M87 is not the only black hole we're interested in imaging. In the heart of our own Milky Way galaxy, 26,000 light years away from us, there's a cluster of stars. And by peering past all the galactic dust with infrared telescopes, astronomers have actually mapped the paths of this cluster of stars over decades. And by tracking the motions of those stars over time, the astronomers have concluded that the only thing small and dense enough to cause this motion is a supermassive black hole. In fact, this discovery led to the Nobel Prize in Physics, given just months ago for the work of Andrea Ghez and Reinhard Genzel, for the discovery of a supermassive compact object at the center of our galaxy, otherwise known as Sagittarius A star. And so as awesome as M87 has been, it turns out that Sagittarius A star, or Sag A star for short, might be able to help us better answer our remaining questions. So since Sag A star is teeny tiny compared to M87's black hole, it's only a measly 4 million solar masses compared to the 6.5 billion. That means that gas orbits around it much more quickly. So whereas it takes 4 to 30 days for gas to make a complete orbit around M87, for Sag A star, gas makes a full orbit every 4 to 30 minutes. And so we'd love to be able to reconstruct a video, actually, of the movie, of the evolution, not just a static image from the data, but actually reconstruct full movies of the black hole evolving. But if you thought recovering a static image is a hard L-pose problem, this is orders of magnitude more challenging because we have the same amount of data, but we have to reconstruct all pixels in a video rather than just a static image. And so as important as it is to continue pushing on the algorithmic approaches to squeeze more out of our data, it's also important to realize that to extract more science, we also have to think about improving not just our algorithms that analyze the data, but also our instrument that collects the data to begin with. And so that is going to lead to the last part of my talk today on using artificial intelligence, machine learning for optimized telescope design. So as I said, in 2017, we only observed with 8 different telescopes, but actually they were only at 6 different locations. And so making images was really challenging with that kind of small number of noisy measurements. So although in the end we were confident in the ring shape, it really took us over a year to build that confidence. And so we've been building out our array to get more data, adding telescopes in Greenland, France, Arizona, and the one I'm most excited about is we recently got funding to add a telescope at Caltech's Owens Valley Radio Observatory. So Caltech is becoming part of the EHT telescope. But imagine what we could do if we added 10 more telescopes. Well, maybe we could actually make a video of the gas falling into the black hole in the center of our galaxy. Being able to do this, as I said, would be a huge scientific gold mine. But before we just plop down a bunch of telescopes, we need to be really careful. And that's because building a new telescope is expensive, at least millions, but usually tens of millions of dollars. And so we really should try to optimize to find the locations that are going to give us the biggest bang for our buck. So how should we go about solving for the location of telescopes in the next generation array? Well, typically the design of the telescopes, where we place telescopes, is idealized and considered independently from the image reconstruction problem. And in doing so, many assumptions are made. For instance, oftentimes nonlinearities in the system are ignored, or complexities in the noise. And especially for problems where the data is so correlated and the noise is so challenging, it's really a huge missed opportunity to not consider them together. And so really we should be trying to jointly optimize the telescope array, the instrument, and our algorithms. And so how should we go about doing that? Well, if you rearrange the blocks in this diagram, you'll notice that it looks very similar to what is called an autoencoder, where the sensing system is the encoder that produces measurements or codes, Y here, and the imaging algorithm is the decoder that recovers back the image. Deep autoencoders, where the encoder and decoder are neural networks, are often used for image compression tasks. And in these tasks, you solve for weights of a neural network that encodes a picture in a small number of measurements, at the same time as a network that decodes those measurements into an image. And so in the reconstruction problem, you could use an arbitrary mathematical function that takes you from the measurements to an image. It just needs to be something that we can code up in our computer, so we can use a neural network for the decoder. But unlike generic deep encoders, sensing systems that we build must obey physical constraints. We can't just write down some mathematical function and then build that math. We can't do that. It has to be something buildable. And so a postdoc in my group, Hassan, has been leading this effort. And the approach that we proposed is to develop a physics-constrained encoder that we can train with the decoder in an end-to-end machine learning framework. So let's zoom into how do we do that. So from an input image Z here, we can define a forward model of the measurements that we expect to collect here. So remember, this forward model is just like a simulation of our telescope. So in this example, we pretend we have 3 possible telescopes to sample, color-coded blue, red, and green, and we indicate the measurements that come from these telescopes as colored dots. These measurements can be complicated, nonlinear, correlated, and noisy, whatever you want. And here we're showing all possible samples. We could pass all those possible samples on as collected measurements to the decoder to make an image, but that would mean we'd actually have to build all of those telescopes to make those measurements. And our goal instead is to choose among them to find which ones are the best to build. So to do that, we introduce what we call a sensor sampling distribution that characterizes the probability that we sample from a particular telescope. We sample telescopes from this distribution, and then we mask out any measurements that were not produced by those telescopes. So now just the red and blue dots remain. And every time we sample from this probability distribution, we sample different combinations of telescopes and obtain different observed measurements. These measurements are then passed on to the decoder that recovers an image from them. So remember that decoder kind of acts like the image reconstruction method. We can string all these pieces together into a single differentiable neural network with trainable blocks highlighted in red. Our ultimate goal is to use this neural network to learn an optimized probability distribution of where to build telescopes, that box on the far left, and we learn that those weights data simultaneously with the decoder, which is that image reconstruction network. And we do that by defining a loss that 1 maximizes the similarity between the input and output images, 2 encourages sensor sparsity. We want to have as few telescopes as possible so that we don't have to build that many. And 3, it encourages sampling diversity to make sure we've explored the space of possible telescope designs. And then we learn the sensor sampling distribution parameters with theta here with the decoder during the end-to-end training. So what is the sensor sampling distribution that we search for? Well, we can use different kinds of distributions, but in this work, we used a fully connected Ising model. If you don't know what an Ising model is, that's no problem. Don't worry about it. Basically, all it is it's a joint distribution over on and off states of the different telescopes. It's parameterized by 2 types of parameters. One that we call site activity, which basically is how important is it to turn one telescope on, irrespective of all the other telescopes. And the other is site correlations, which indicate if a particular telescope is turned on, if it's better to turn another telescope on or off. Why would you want to turn a telescope off? Well, to save resources. We want to be able to find the smallest set of telescopes that performs well. And so we use end-to-end training that is going to basically search for the best model parameters theta here. So here's an example of a telescope distribution that we have learned. The Ising model parameters theta jj here on the left quantify the activity or the importance of any single telescope, and the model parameters theta jk on the right quantify the correlations between pairs of telescopes, where red represents positive correlations and blue represents negative correlations. And from the recovered distributions, we can see some patterns that we'd expect to see. For instance, in the case of uncorrelated noise, in the case of simple noise, in many cases, co-located telescopes are heavily penalized from being sampled together. And this makes sense because in the case of simple noise, those two telescopes are basically taking the exact same measurement. So why would you take the measurement twice? You would want to use your resources to get a new kind of measurement. But my favorite is not the things we would expect to see, but the things we don't know what to expect. So for instance, by changing the types of noise that we train on, we can also see how the noise that enters our system affects the results. For instance, this result is with purely Gaussian thermal noise included. But when we include the difficult atmospheric air that plagues our measurements, it scrambles our data, as I talked about earlier. The array preferences change drastically. So different telescopes are preferred under different kinds of noise distributions on the measurements. And so notice that when I flip back and forth, the correlations have changed. And we find this tells us about structures in the geometry that are preferred in the case of this challenging atmospheric noise. And complicated and correlated noise is not something that people can easily consider analytically through ideas such as compressed sensing. And so I'm really excited that our method like this is able to handle this much more complicated and realistic noise models and learn from them. And so using this approach, we're starting to understand where we may be wanting to place our next ground-based telescopes to reveal more of the unseen. And I'm also excited that we soon may be applying it to a variety of other scenarios, including even the optimal placement of telescopes in space. So to close, it's clear we've learned a lot from this image of the black hole in M87 already. But what I hope I got across in the talk today is that really we're just at the beginning. And now that we have this new extreme laboratory of gravity, we're already thinking towards the future in ways that we can improve our instruments, improve our algorithms, improve them jointly with ideas from AI to learn even more. And hopefully one day not just show you a static image of a black hole, but a movie of a black hole as its gas is slowly falling towards its event horizon. So with that, I want to thank the amazing team of collaborators that I have the opportunity to work with on a daily basis. Far too many to name, but I want to highlight in particular Huff for leading the work in the second half of the talk on the optimized telescope design. And I also want to especially thank all the early career collaborators who are often behind the scenes, but do all the hard work to make the Event Horizon Telescope project a success. So thank you. I'm happy to take any questions that you have.